All right, welcome everybody to our Let's Talk Meshing webinar. In this webinar, we're going to be discussing overset grid generation and CFD using Pointwise, Suggar++, and Caelus. Now joining us today is Dr. Ralph Nowak. Dr. Nowak is the president of Celeritas Simulation Technology, and he is the primary developer of the overset grid assembler Suggar++. He's been developing CFD solver, grid generation, and overset technology for the last 35 years. Over the last 15 years, he's been developing Suggar++ and related software. Now, Ralph has actually prepared a pre-recorded presentation for us this morning, which we will start out with for the webinar, and then he'll be joining us live for the Q&A portion at the end. So thank you for joining us, Ralph. We also have with us Dr. Chris Sidoroff. Dr. Sidoroff is the Managing Director and Principal Research Engineer at Applied CCM Canada, a company that provides development, technical support, and training for open source-based CFD software such as Caelus, the solver that they've developed, and OpenFoam. So thank you for joining us, Chris. And myself, my name is Travis Kerrigan. I'm a senior engineer with Pointwise, and as well as doing webinars like this and webcasts and attending conferences, I work with clients to help strengthen their CFD process by introducing them to Pointwise and develop interactive and automated solutions for them using our software and our glyph scripting language. Now, to give you a little idea of where we're going today, this is going to be a packed webinar. We've got a lot of great content to share with you. For the first 10 minutes, Ralph is going to give us an overview of the overset grid approach, followed by an introduction to Suggar++ and its capabilities, and then he's going to talk a little bit about his company, Celeritas Simulation Technology. After that, for about 10 minutes, Chris Sidoroff is going to introduce us to his company, Applied CCM Canada, and introduce us to Caelus and a CFD solver that they've developed. It's a fork of OpenFoam, which he'll talk about, and the motivation for overset CFD, as well as the implementation of overset in Caelus. After that, for about 30 minutes, we're going to pull up an actual application in Pointwise, and we're going to walk through the overset grid generation process in Pointwise itself, set up the inputs for Suggar++, and show you how you could export everything to Caelus. And Chris is going to come back and show us what that looks like in the Caelus environment and walk us through some preliminary CFD results. Okay. So with that, give me just a moment and I'm going to prepare Ralph's recording. 1 second.
Hello, I want to first thank Travis and Pointwise for allowing me to participate in this webinar. I'm really excited about the Pointwise OGA interface, and I think it will really help people doing overset gridding and simulations. I will start with a brief overview of the overset grid approach for those that might not be familiar with it, followed by an overview of the capabilities of Suggar++. In the overset grid approach, we begin by discretizing the domain with a set of overlapping component grids. These component grids can be generated about a complete body or a portion of a body, such as the bare ship hull or aircraft fuselage, a wing, a wheel, a fin, etc. They will be constructed mostly independently of each other. That's a real advantage, as we can focus locally and generate good quality grids locally without having to pay detailed attention to how these local grids fit with other portions of the body. The first step in the overset grid assembly process is the overset hole cutting. This step is going to identify the points that should be excluded from the computation, or what we call out or hole points. Because we've generated these grids locally without detailed consideration of other body components, a component grid may extend inside a different portion of the body or behind the symmetry plane. These points outside the domain of interest are obviously not valid and must be excluded from the flow solver computation. You can see in the picture the blue points that we have marked as hole or out points that are inside the airflow. Once we have the holes, the next step is to identify the intergrid boundary points, or as we call them, fringe points. These are the locations that are new boundary condition points that will couple the solution between the different component grids. The flow solver will see a specified value boundary condition at the fringe points, and that specified value will be provided by interpolating the solution on a different component grid that overlaps the fringe point. So you can see in the picture the blue hole points, and surrounding them are the black fringe points that provide boundary values to couple the solution from the airfoil mesh to the Cartesian mesh. You can see the red dots, which are the fringe points at the outer boundary of the airfoil mesh, and these fringes will couple the solution from the Cartesian mesh to the airfoil mesh. That provides a valid overset assembly and set domain connectivity information to be used for a flow solution. We can improve the quality of the flow solution by reducing the amount of overlap between component grids. The only real guidance with this minimization procedure is the fringe and interpolation source or donor should be about the same size. So you can see we've marked as holes more of the Cartesian mesh surrounding the airfoil and moved the fringe boundaries closer together. The solution quality is improved since it is not propagated over the same region on different component grids with different resolutions. Now I'd like to look at some of the benefits and new capabilities that are enabled when using an overset approach. One of the first things that overset grids was used for was to simplify grid generation on a complex geometry. We can decompose a complex geometry, such as the ship hull, into different components. We grid the bare hull first, and then incrementally add the more complex geometric components. This has the benefit of not only simplifying the grid generation, but naturally allows you to identify the effect of each component on a performance measure. Find the drag of the bare hull, and then add the skag or rudders without changing the previous grids. Run the simulation again and be able to predict the change in the performance measure caused by adding the geometry component. Another example is shown by this notional turbine blade, and we want to optimize the placement of many cooling holes. See only one here, but think of the whole blade with lots of holes. The number and placement of the holes using overset grids can be controlled by an optimizer, and we don't have to regrid the entire configuration, but simply use the flexibility of the overset assembly to add the cooling holes in the appropriate locations. One of the big capabilities that overset grids provides is to enable relative motion. In this case, we have a component grid for the helicopter fuselage and a single grid that is duplicated for each of the rotor blades. The moving body rotor blade grids will move with each blade and not require regridding to accommodate the motion. Flexibility and deformation of the rotor blades can also be accommodated within the overset assembly process. The important thing is that we don't have to regrid, but simply need to recompute the overset domain connectivity at each time step. On the right is a slice through a ship simulation where the ship is pitching, heaving, rolling, etc., along with rudders and propellers moving. Each component grid is fixed to its geometry, maintaining a good quality grid locally, and the overset domain connectivity information is again recomputed at each time step. In order to do all of that, we must have the software to compute the overset domain connectivity information. Suggar++ is such a product, is available from my company, and is really the only software in the world with its full set of capabilities for overset grid assembly. It is exportable under an EAR 99 license, so we can provide it to most customers in the world. Its development has been based upon extensive experience and interaction with a lot of different customers, flow solvers, and simulations. So it has a lot of capabilities to meet your simulation needs. As I said before, it is also integrated with the Pointwise OGA GUI, which lets you build the grids within Pointwise, set up the inputs and run Suggar++, then visualize the overset connectivity information within Pointwise and provide you with the feedback to improve your overset grids. So there's a nice tight integration with the overset grid generation and overset grid assembly processes. Suggar++ supports basically all the grid types that you need: structured curvilinear and analytic grids, the usual unstructured grid topologies, including general polyhedral grid. Suggar++ supports node and or cell-centered assemblies and has even been used to couple different flow solvers. In one example, a structured node-centered solver was coupled to a cell-centered unstructured octree-based solver through the use of the Suggar++ computed overset domain connectivity information. It also has advanced support for structured grid solver by allowing an arbitrary solver stencil. For one run, you can tell Suggar++ that you will only need an inviscid solver stencil, and a different run, you will need a full viscous stencil, and the fringe requirements will be adjusted appropriately. Suggar++ also has support for higher order solver discretizations. It can provide an arbitrary number of fringes that may be required for your high order flow solver stencil. Arbitrary high-order interpolation is also available for structured grids. Suggar++ has a variety of methods for hole cutting to provide the flexibility, accuracy, and speed that you need for your simulation. It has an overlap minimization process that uses a concept I call the donor suitability function, or DSF, that tries to answer, is this donor suitable for or the best for this fringe point? The DSF can be found to be geometry-related quantities such as element, volume, edge length, etc. There are cases where one type of DSF will work better than another, and we have the options to give you the assembly that meets your requirements. We also have a unique new capability where the DSF can be set to the distance to the wall. Powerful hybrid capability is to use one metric, such as volume for the most of the field, but switch to distance to the wall near the surfaces. This really helps maintain a good assembly when we have highly stretched meshes, especially in small gap regions. Suggar++ also provides support for overlapping surface meshes. The first part of this we call surface assembly. This projects the fringe grid onto the donor grid so we can obtain correct interpolations near the body. This works with structured grids and also unstructured grids with layers. In addition, if you need to compute force and moments by integrating on the overlapping surfaces, you need to eliminate the double counting that would result. Suggar++ computes weights that you can use in the surface integration to provide accurate integrated values. Suggar++ has a parallel execution capability using threads for shared memory machines, MPI for distributed memory machines, and a hybrid capability where you can distribute across distributed memory nodes using MPI and use threads within each node. There's also an integrated decomposition capability to break the grids into smaller subgrids for more improved parallel efficiency. Suggar++ is designed for moving body simulations to efficiently recompute the DCI at each time step. It's available as a library to link in the flow solver to provide a tightly integrated dynamic overset grid assembly process. The library provides calls to control its execution, obtain the moving body information, and transfer the DCI back to the flow solver. It now includes an implementation of the DirtLab capability, which is another library I developed years ago, and is made available within Suggar++. Using the DirtLab capability can simplify the addition of an overset capability to a flow solver. Celeritas Simulation Technology is solely focused on Suggar++. We are continuing to develop and improve the software and provide commercial distribution and support for it. You can get more information from our website shown on this slide. We recently signed Applied CCM as distributors of Suggar++ and are very excited to be working with them. Through their efforts, the OpenFOAM community will have a releasable interface to Suggar++ and a powerful overset simulation capability. Thank you for this opportunity to introduce you to the benefits of overset grids and the capabilities of Suggar++.
All right, so we appreciate Ralph putting that together for us. As I mentioned before, Ralph is signed on with us. He'll actually be joining us at the end for our Q&A session. So with that, I'm going to pass things over to Chris Sidoroff, and he's going to start by talking a little bit about Applied CCM. So Chris?
Thanks, Travis. Yeah, so I'd like to start with just a quick introduction to who we are and what we do. So I think Travis mentioned a little bit of this at the beginning. So my company, we specialize in the application support, and also we do a significant amount of development around anything OpenFOAM based, including Caelus, which I'll talk about here in a minute. I'm located in Canada. My primary business partner, Darren Stevens, is located in Australia. And we also have a technology partner, Alex Jemkov, in the US. So, our primary mission, the mission within Applied CCM, is to engage with customers as our technology department. So what does that kind of nebulous statement mean? I mean, I think this little diagram that we like to use at the bottom of the slide kind of really explains what we try to do. Is we're trying to kind of fill that gap between traditional academic research, basic research, and how the industry wants to adopt and apply these technologies. As we kind of come in and kind of use our strong technical backgrounds to kind of move technology from applied research all the way over to into more mainstream usage. So that's kind of where we're at. I mentioned we're the main developers of Caelus. I'll explain that in the next slide. And then, like Ralph mentioned, we are also very excited to be become distributors of Suggar++. And our motivation for doing that is obviously to provide a kind of an end-to-end solution for doing overset simulations with Caelus, and clearly Suggar is the a necessary component part of that process. Okay, go ahead, Travis. So what is Caelus? Travis mentioned for me earlier that Caelus is a fork of OpenFOAM. Like OpenFOAM, it's free and open source. There's the URL for it where you can go and download it. There's also a little bit of an explanation, some of the philosophical reasons for our forking of OpenFOAM and creating Caelus. I'll maybe kind of highlight some of the technical reasons here. So first of all, I'll just maybe mention the numbering. We have these periodic releases. They're twice released, April and October, and the initial numbering, so 410, that represents like the year. So the year 2014, we just dropped the 1 for simplicity, and then the 4 represents the month, April, or 10 represents October. So our very first release was last October, so 2014, and again, probably the biggest reason for creating it was to be able to enable multi-platform support, and particularly for Windows users. I mean, we didn't want Windows users to be relegated, to kind of second-class citizens in the the OpenFOAM world. So what we've gone and done is we've fully ported Caelus to Windows as well as Mac. It's a little more kind of natural since it's quite similar to Linux, which is very Unix-like. Really to facilitate that, we've replaced the build system, and we've used a very broadly and largely used a build framework called SCONS or SCONS. It's Python-based. We've also added an installer for it. It's a little GUI installer. It also works in command line, but the default is to work as a GUI. Very easy to install, almost no dependencies. I think the only 2 dependencies, at least on Windows, is MPI and Python, and then I guess therefore on Mac and Linux, probably really just MPI. The other one we've done is we gutted the turbulence models and rewrote them per the most commonly used variants in open literature and provided some validation for them. And as well as we started, a documentation validation project, and that's also, there's a link to that on the Caelus website. Earlier this year, the April release was about algorithmic improvements on non-perfect meshes, some improvements for accuracy near boundaries on non-perfect meshes as well. Another really cool one we added was from a project called SWACRaFOAM by Bernard Gescheiter, which was kind of an independently developed project by himself and through his company. And what that enables is expression-based, like boundary conditions, initial conditions, in simulation, post-processing, all sorts of stuff. So it's a really useful library. And so we've integrated that directly into Caelus, and as well as some Python wrapping that will help kind of facilitate the automation of that through Python scripting, which is really popular in the HPC world. The last October. Just previously in October, we released version 5.10, and the big new features in that was compressible solvers and turbulence models. In fact, up until that release, we had no compressible capabilities. We completely removed all the previous ones in the initial release, and we rewrote from scratch our own compressible solvers, and then re-implemented all the turbulence models with the correct compressible variants. And then there was a assortment of other numerical improvements, and then another big one we added was a new turbulence model class that we developed called VLAS, which is an improvement on DES, and I've been tweeting about and kind of making a bit of noise about a paper we published on that recently at an aerospace conference. So you can contact me if you want to find out more about that. So go ahead, next slide, Travis. So I mentioned the documentation. So this is the snapshot of the website with the documentation. We use the Python Sphinx project as the documentation framework. So you know, very nice looking mathematical rendering and stuff like that. And then the actual installation GUI itself. So next slide, Travis. So getting back to the topic at hand, so why Overset CFD? I think Ralph really highlighted a lot of the benefits, you know, very succinctly and clearly, and why it's a very powerful technology. So I'm just going to maybe kind of talk about it a little bit with respect to the application that Travis is going to demonstrate here in a few minutes. I think the big one is, you know, at least in my mind, is higher quality meshes in less time. I mean, I've been involved with CFD in some capacity or another for almost 15 years now. You know, and despite the overwhelming movement of the industry to go towards unstructured meshing and unstructured solvers, you know, there still seems to be, you know, at least from my viewpoint, a lot of people still want to use structured meshes, and for a variety of reasons: accuracy, simulation time, all this kind of stuff. But you know, for industrial scale problems, you know, they're just too time consuming to make, even for experienced users. So I mean, really, Overset really reduces that burden, because like Ralph talked about, you make these meshes on a component level or on a portion of the component level, and the Overset grid assembly process is really what takes care of the connectivity between the component grids themselves. Okay, next slide. So another big one, I think this is, you know, you'll often see a lot of really good, you know, interesting applications of Overset for the kind of the higher end usage, but I really want to talk about, you know, the high quality stuff, as well as this is another big one, why Overset is really powerful. And this is just in regards to like static meshes. We're not even talking about moving meshes at this point, is the high quality. And then this is another big one, is adding and removing details without changing the baseline grid is really important, particularly when you're looking at you know, influences of a particular piece of geometry. Was it because we introduced the geometry, or is it because the background mesh changed? Well, with Overset, the background mesh doesn't need to change, and so it's, you know, a much more precise way to be able to look at this kind of stuff. I mean, here I'm just, maybe it's a bit of an exaggerated example, but the idea is that when I remove the wheels, you can see that the body mesh on the car and the background meshes don't change. The addition or removal of the wheels is you know, solely handled by the Overset grid assembly process for Suggar. Okay, next slide, Travis. And another good one, kind of along the same vein, is maybe not necessarily moving or adding geometry, removing or adding geometry, but actually is repositioning it. And so you can imagine this is similar to the turbine blade cooling hole thing that Ralph was talking about, is actually repositioning in geometry. So here I'm just, again, artificially changing the right height of the car, and I don't have to worry about, you know, deforming or, you know, or reconnecting the grid, because the Overset it takes care of that itself. So again, we don't have to change the baseline grid. The grids in the car move with the car, the grids on the wheels stay the same, the background grids stay the same. So you know, a very consistent approach, and it just naturally facilitates this kind of work. Again, it could be very natural to be use it with an optimization problem. Okay, Travis. And then we get into the more, you know, typical applications you see Overset used for is, well, this one is a prescribed motion. Again, this is a bit contrived. I mean, the wheel in this case is actually symmetric, so I don't necessarily need to actually physically rotate the wheel. I could just apply a rotating velocity boundary condition. But you can imagine on a real wheel that has, you know, the actual wheel that's got spokes, and maybe there's a valve stem and a brake caliper and a brake rotor, and then racing cars have ducts and all sorts of things, and it gets really complicated. And you know, how do you incorporate those kind of details? And particularly if, you know, the geometry is moving around and all this kind of stuff, it just may not even be possible to even do this with any other approach. I mean, maybe another typical approach for doing rotating is to, you have one region is moving, the other region is static, you have some interface grid, and that interface grid necessarily needs to be cylindrical. But in the case of this wheel, it'd be, you know, it might be very difficult to stick in a cylindrical set of patches to be able to facilitate that interface. So, and that's not necessarily the Overset. So, you know, you can overcome some of these traditional difficulties. Okay, next one. And then, you know, Overset just naturally handles these more more complex cases where you have unconstrained motion, where the motion is driven by the surface forces through an ODE solver. I mean, YouTube is littered with all sorts of beautiful looking animations in FlowViz that show this, and this is the one from Ralph's website, which is on our tumble home. It's the boat is going through some sort of maneuver, and due to the forces on the boat, it's broaching, and and I think the big one you can see here is adding these smaller details like the bilge keel. Again, that's static, but I mean the ability to add it in is kind of much simplified. But the big one really is the to be able to rotate the rudders as well as the spinning propellers. I mean, so they're very difficult to do with any other kind of other approach. Okay, go ahead, Travis. So the overset in Caelus. So I want to make very clear that there will be, again, Caelus is a fork of OpenFOAM. It functionally operates like OpenFOAM, and there will be no change in the regular usage of Caelus to facilitate overset. So what I mean by this is the runtime selection mechanisms that people are really familiar with and like in OpenFOAM and Caelus, those will be still completely functional. The other one is the file format is completely compatible. There's no change in the file format, so post-processing, all that kind of stuff will remain unchanged. Again, to the user will be just really under the hood. Now the process for doing at least the static and prescribed motion cases, the overset grid assembly process is purely a pre-processing step, just like the meshing. So have them laid out here 1, 2, and 3. So generate the mesh, run Suggar, run the solver, and in fact I could probably, with the stuff that Travis is going to talk about the Pointwise Suggar integration, really if you're using Pointwise, step 1 and 2 are really step 1A and 1B, because Pointwise is where you can set up and execute Suggar and examine the results. So it's really just a two-part process with Pointwise. And then 6DOF requires the overset grid assembly on the fly, and so with that you'd have to, the solver will be linked directly with Suggar. Now, before I pass things over to Travis to talk about his mesh demonstration, I really want to emphasize the fact that one of the major reasons I think that the commercial world companies and the industry is looking at OpenFOAM as a serious way to do their simulation is because there's no limit on the number of parallel processes, and neither of these approaches, either the static prescribed motion or the 6DOF, which requires the library version, will put any limit on the number of parallel processes the user can use. So that benefit will remain. So anyways, with that, I'll pass it over to Travis, and he can get going in his part.
All right, thanks, Chris. Okay, so I've just pulled up Pointwise, and so now we're going to talk a little bit about those 3 steps that Chris mentioned in Pointwise, and how Pointwise kind of brings all of these steps into one unified environment. So within Pointwise, you can not only generate your overset grids using the standard tools that Pointwise offers for grid generation, but you can also set up the inputs for your overset grid assembler, in this case Suggar++, and then export everything to your CFD solver, and in this case we're using Caelus. So this is the application that we're going to be looking at. This is an external automotive application that Chris Sidoroff prepared for us for the purposes of this webinar. It's a fully overset mesh. It's all structured, so hexahedra only, and everything is overlapping. So that's one thing to note. And I figured what I would do to start is maybe walk through and show you some of the characteristics of this mesh. And then I'm actually going to add a component into the mesh, generate a block, and then add it into the overset grid assembly for Suggar++. So you'll notice that, for example, on our surface, all of our surface grids are overlapping. So I've just selected 2 structured surface meshes in Pointwise. And in Pointwise, you create these just like you create any other, domain, or what we call a domain, which is a surface mesh in Pointwise. You'll notice that they are overlapping by 6 or more cells, and that the cell areas are roughly equivalent in the overlap locations. Okay. Now, once you've created those overlapping surface meshes, the next step is to create your overlapping volume meshes. Now, typically this is done through extrusion, either algebraic or hyperbolic extrusion, taking advantage of the splay option, where when you grow off of the surface, you're kind of mushrooming out so you can get sufficient overlap in the volume. And that's exactly what Chris has done for this case. Is the majority of these surface meshes, he's just done a hyperbolic extrusion. And the nice thing about that is, in Pointwise, if I take a block that I've extruded, like the block on the side of this vehicle, and go to grid re-extrude, I can push that block out even further. So for example, after say I run the assembly and I find that maybe there's some orphan points, and remember Ralph's talk, an orphan is basically a fringe without an acceptable donor, and that could be because maybe we don't have acceptable overlap in that particular region. I could come in here and just push out that extrusion a little bit more so I can get sufficient overlap and then rerun the assembler. I could also just restart the extrusion from scratch. Maybe I'm targeting a different Y plus value, so I need to specify a different initial spacing or a different growth rate or something like that, and then just redo this extrusion, okay? So once you've got all of your overlapping surface meshes and you have your overlapping volume meshes, then the next step would be to set up and execute your assembler and then visualize the results, which is also something that you can do within Pointwise. So I'm going to go ahead and isolate one of these blocks. So this is the near field Cartesian block, and go to the examine menu. And I'm going to take a cut through here, and you can see the result of that whole cut operation. We've actually already run the assembler on this problem, so you can see the results of that operation. And what you're looking at is that background mesh is being trimmed by not only the vehicle body, so you get an idea of what the shape of that vehicle looks like, but also the wheels. This little chunk up here was done through a manual hole cut operation to effectively reduce the cell count for the overall composite grid. But you can see, I mean, that's effectively what's happening when you run the assembler. You're cutting out bodies from different bodies. Okay. Now, one of the things that I can look at is I can look at the fringes on a cutting plane, which is kind of cool. You can see, again, fringes are cells that have donors, so they're going to receive solution information from other bodies, and we can see those fringe locations. We could also identify any orphans if we had any and get in there and mitigate those problems. Okay. Now, one thing I want to point out is back here at the wheel location. So you'll notice that the background grid not only is being trimmed by the car, but it's also being trimmed by this wheel, which is a separate body as well. I'm going to go ahead and bring the wheel volume into this as well and take the same cut. And you can see that that wheel volume mesh is being trimmed by the vehicle body. Okay, and if we were to change the ride height, it would trim in different locations, but it's also being cut by the background grid. And so down here in this corner, we have this void because these two bodies are trimming each other and we're left with a void. Now, what we typically use to fill voids like this is called a collar block. And the purpose of that collar block is to grow off of both of these surfaces, the wheel surfaces and the ground plane in this example, simultaneously to fill a void left by two intersecting bodies. Okay, so I'm going to go ahead and bring in a collar block so you can see, take the same cut and you can see what that collar block does. Again, it fills that void, it provides the resolution we need off of the wheel, the resolution we need off the floor. So like Chris mentioned, you can do a lot with static overset cases. You know, we can add complexity, we can bring in these wheels, we can change the ride height by just translating the entire vehicle body up and down. We could say change the weight of the vehicle and the location of the intersection of the wheel and the ground plane. And in doing that, all we would need to regenerate is that collar block. And so to demonstrate that, what I've done is I've brought in the front wheel. I've actually pulled it out of the overset assembly and I brought it back in. So we could imagine we've meshed this in another instance of Pointwise. And I've got my overlapping surface meshes. I've got my overlapping volume meshes. Maybe we've changed the weight of the vehicle and we need to re-intersect this wheel with the ground plane and regenerate that collar block. And again, that's all we would have to do for this assembly. So I've already gone ahead and intersected it with the ground plane. What I'm going to do is I'm going to create that collar block. I'm going to demonstrate two surface constrained extrusions and the creation of that collar block, and then we're going to walk through the process of adding it to the overset grid assembly. So first thing I'll do is create some grid curves on my intersection curves that were created. Okay. The next step is I will grab those grid curves and I will perform one surface constrained extrusion on the wheel. So I'll go ahead and set up my initial spacing and my growth rates. I'll pick my orientation and I'm going to specify this to be database constrained and just select my wheel surfaces. So this extrusion will be constrained to the wheel geometry. I'm going to turn down my volume smoothing to preserve the spacing of that initial front, and run the extrusion 25 steps. Okay, I'm going to come back and I'm going to turn down my growth rate. So you have a lot of control over this. And the reason I'm turning it down is to equalize the area of those elements in the overlap location, and run this for 10 more steps. And you can see I have sufficient overlap, and those cells are roughly the same area as the underlying cells that are already on the surface of that wheel. Okay, so I'll go ahead and accept that. And I'm going to do another surface constrained extrusion. This time it's going to be constrained to the tunnel floor, all right, the ground plane. So I'll go ahead and set up my initial spacing, my growth rate, and reorient and set my extrusion direction, turn down my volume smoothing again, and run this for 15 steps. And then I'll come back and do the same thing I did before. I'm going to turn down my growth rate to equalize the area of those elements and run that for 10 more steps. And you can see the result of that operation. So I ended up with 2 surface constrained extrusions. Now, typically at this point, what you'll do is you'll grab both these domains, as I've done, and do a hyperbolic extrusion to get that collar block in one step. However, in this case, we can't do that. The reason being, this angle is just too shallow. Okay, the normals coming off the wheel and the normals coming off the ground plane are going to intersect, and we're going to get pinch points, and we're not going to get nearly enough layers in that region. But that doesn't mean we're stuck. Okay, I don't have to create all of my blocks through extrusion. I can actually create blocks manually as well. So that's exactly what I'm going to go ahead and do. I'm going to manually assemble this block, this collar block. So I'm going to grab this connector and copy and paste and translate it in the vertical direction. So we'll go ahead and reorient and translate it to about right there. Okay. And now I'm going to stitch the topologies together and build up the domains for my block. Okay, so this connector needs 26 points, and this connector needs 36 points. And I can grab all 4 of these connectors and build my domain. All right, so now I've built this domain, and you'll notice that in building that domain, these connectors aren't really distributed properly. The grid points aren't distributed properly. I'm not getting any sort of resolution off the wheel or the ground plane, and so I can go ahead and just copy the distribution from the opposing connector. That'll save me a little bit of time. So I'll go ahead and copy the distribution from this connector over here. And now if I take a look at that domain, you'll notice that I get the resolution off the wheel and I get the resolution off the ground plane as well. Okay. The last step is to create the remaining domains, and then I can assemble my block. So I'm going to go ahead and create a domain. So we'll go ahead and flip that. So there's one domain, and pick our second domain. Okay, and there's our second domain. And the last step is creating my block. So a structure block consists of 6 faces. I'm assembling this one manually because one of the faces is actually going to be used twice. So I'm basically going through and picking the 6 faces of my structured block. Okay, and I've got my structured block. And now if I go examine, say let's examine the minimum included angle, we notice the minimum included angle is 26.8 degrees, and we know exactly where that's going to be. It's right here in the corner, and that's acceptable. And you'll notice that the grid quality for this block is pretty good, and we were able to build it by hand and not have to rely on the extrusion to get out only a handful of layers. Okay. All right, so that's how you can go ahead and assemble a collar block. All right, so now what I'm going to do is I'm going to add it into the assembly, the Overset grid assembly. But before I do that, we need to talk a little bit about how to set up your Overset environment. So the first thing you would want to do is go to Edit, Preferences, and in the Overset section, you'd want to specify your case directory. And this is where all of the grid files are actually going to be stored when you run the assembler. Okay, this is also where you can specify if you want to run your assembler locally or remotely. Once you've done that, you'll go to Grid, Overset, and the Attributes tab. This is where you'll pick your assembler. In this case, we're using Suggar++, and we've given our case a name called Sedan, and we'll get a folder after we run Suggar++. We will get a folder called Sedan in the directory that we've actually specified in the preferences. And now the last step is to go to CAE set boundary conditions. So we've actually built our grid. We've got all of our components and we've got all of our volume meshes. Now we need to set up our boundary conditions, not only for the flow solver, but also for our overset grid assembler, Suggar++. So we've already gone and specified all of the boundary conditions, so I don't have to type out all of these during the webinar, but there are 4 entities that I've just created that don't have a boundary condition assigned to them, so I can go ahead and create them. But before then, I want to mention the CAE type. These are going to be your flow solver boundary conditions, and because the type is OpenFoam, these are going to be OpenFoam specific, so things that you're familiar with: patch, wall, symmetry, plane. This is the stuff that's going to go in the boundary file in your polymesh directory. This other column here, this overset type column, this is where you're going to specify your overset boundary conditions. So solid patches in different bodies are going to cut solid patches in other bodies. So you need to be able to specify that here, and also symmetry, far field, and overlap. So those are the different overset types you'll be using and that we've used for this application. Okay, now like I said, I just created 4 new entities and I need to assign those to the appropriate boundary conditions, so I'll go ahead and do that. I'm going to select the domain that I created that's on the ground plane and put it in this ground collar boundary condition. Okay, this is a solid overset type, and we'll just take note of this name because we're actually going to need this in just a little bit. So ground collar. I'm going to select the domain that I created on the surface of the wheel and assign it to the wheel boundary condition, and you'll notice that when I highlight that, all of those domains are in that boundary condition. And then the last 2, I'm just going to add to selection and put those in the overlap boundary condition. Okay, so we're done assigning boundary conditions. At this point, everything is set up so that we can basically specify our inputs for Suggar++. And we do that by going back to the grid overset menu. Now, before I go into the attributes tab to show you the inputs, I wanted to point out the statistics. You'll notice that most of these blocks are up to date, some are not. Like I said, we've actually run the assembler on this problem. Some of the blocks are not up to date because what I did is I just pulled the wheel out of the assembly and we're going to add it back in. Okay, so I deleted the collar block, I pulled the wheel out of the assembly. We're going to add it back in along with that collar block. But the nice thing about this is you can see what blocks are up to date, what blocks aren't, and you can see the holes, the fringes, the orphans, and you can persistently display that information as well. So for example, I can turn on fringes and I can see the fringes. I could turn on the holes, see the holes. And if I exited this panel, I could still see that. The nice thing about that is if I had orphans, which I don't in this case, I could persistently see where those are, and I could get out, maybe push out an extrusion a little bit more to provide some sufficient overlap or mitigate those problems by building additional entities or whatever I need to do to get rid of those orphan points. So that's really nice. All right, so in the attributes tab, this is where you're going to set up your inputs for Suggar++ in this node tree. Now you'll notice that there are quite a few nodes here already. We've got things like cell-centered, because this is a cell-centered solver. We picked our solver stencil, some interpolation settings, our symmetry plane, hole cut method, etc. These inputs are specific to Suggar++, and so if you have questions about these, I encourage you to ask Ralph. Again, he'll be around for the Q&A, or afterward we will provide email addresses where you can reach us. But I do encourage you to contact Ralph if you have questions about some of these Suggar++ specific inputs. Okay. The other thing I wanted to mention about this node tree is you can see that there are quite a few things here, and more often than not, you're probably going to reuse most of this stuff from case to case. Okay, as long as you're not changing too many things, you're probably going to reuse most of these inputs. The nice thing is if I exit this panel, I could go to File, Save Environment As. Okay, and what saving the environment will do is it'll basically save a Pointwise file without the grid. Okay, it'll actually save this node tree without the grid. So if I'm starting a new overset problem, I could just load that environment file and start working on a mesh, and all of these inputs would still be here, and I could maybe modify the ones that I need to modify for that specific case. So I don't have to start from scratch each time. Okay. All right, so the first thing I need to set up is in the output node, composite grid. I need to give the composite grid a name. You can see that we've given it composite.foam. In the Sedan directory, I'm going to get a composite.foam directory that has the polymesh directory with all of the associated grid files for OpenFoam, in this case also for Caelus. And we picked the style foam, and that's what we're going to end up getting in the composite.foam directory. And so that's one of the pieces of information that Caelus is going to need. The other piece of information is the domain connectivity information. We give it a file name, output.dci. The style is DCI for domain connectivity information. Again, the polymesh directory and this one file are the only two things that we'll need to pass to Caelus to run an overset grid simulation. And those are going to be generated when we actually run the assembler. We don't actually have to export anything. We just run the assembler and it's going to generate all those files for us, which is really nice. Okay. The last thing you'll set up are your bodies. Okay. And you'll notice that I've got a number of bodies already. I've got my root body. I've got my tunnel body. So I'll highlight it in green. I have a car body highlighted in pink, and then a rear wheel body. Now you can think of this, again, this is an assembly of components, okay? So each one of these bodies is like a part in that assembly, all right? And one of the things that's missing is the front wheel, all right? I need to go ahead and add that front wheel to this assembly. However, there's a lot of stuff going on in the display right now, and coming in here and picking the blocks, it's possible, but it could be tedious, particularly if we were looking at something even more complex. So I'm going to go ahead and exit this panel and show you something that's going to save you quite a bit of time. I'm going to go ahead and isolate my wheel block. Let's say we've just created this, okay? When you just create your volume meshes for a particular component, go ahead and select all of those blocks and create a group. In this case, I'll call it front wheel. And in the list panel, you can see your groups. And if you select them, it not only selects that group, it selects all the entities within that group. And you'll notice that 4 out of 8 blocks have been selected. Just by clicking on that group, all of those blocks are automatically selected, which is really handy. All right, so I'm going to go ahead and toggle everything back on. We're going to go back into Grid Overset and go to the Attributes tab. And I'm going to create a new body for the front wheel. So to do that, I'll click on the root body. I'm going to go back to my list panel and click on my group. It automatically selects all of those blocks. Come back to Overset and say New Body. And a new body is created and it automatically assigns all of those blocks to that body, which is really handy. So I don't have to create a body and then add the volume meshes one at a time. All right. The next thing I need to do is change this from structured to unstructured. So we change it to the style to Cobalt for the blocks. Just really quick to go through there and change those to Cobalt. And the last thing I need to do is properly handle this collar block, right? So you'll notice, oh, and probably the other thing I should do is change this to front wheel. Give it a name. All right, so we've got the body front wheel with its blocks. And this block, you'll notice, actually has a domain or a surface mesh that's sitting on another body. Right, so most of these bodies, all of these bodies actually are self-contained. You'll notice that the car body is the car body, but the front wheel body has a domain that's actually sitting on the tunnel body. So we need to tell Suggar++ how to handle that. So I'm going to go ahead and right-click on the collar block and add a boundary surface. Now you notice that there's some other inputs in here, some custom cutters and things like that. Again, if you have any questions about that, please feel free to ask Ralph. I'm going to go ahead and pick the boundary surface. And I need to give it a name. Now, this name is the same name as the boundary condition that I mentioned in that boundary condition in the CAE set boundary condition panel. So it's called ground collar. And that's the boundary condition that contains the domain, that surface constrained extrusion we did that's on the tunnel body. And once I specify that, I right click on here and add a collar and say that that domain is associated with the tunnel body. And that's the only bit of information that I need to provide for Suggar++ to properly handle that collar block. So at this point, I'm done setting up my inputs. I've added the front wheel body, I specified the collar block, I can come back to the Assemble tab and click Run. And again, when I click Run, it's automatically going to create those directories. I'm going to get that polymesh directory with my grid files for Caelus, get my output.dci file, the domain connectivity information, and take those two pieces of information and pass those along to Caelus. So with that, I'm going to pass things back to Chris, and he's going to start by showing you what that looks like in the Caelus environment. So Chris?
Yeah, thanks, Travis. Just to kind of quickly follow along with what Travis was talking about. So when you run Suggar++ through Pointwise, you're gonna, depending on where your default directory is, in my case, I set it up to just /dmp on my Linux workstation. It's gonna, the output of Suggar, well, both the input required to run Suggar and the output that Suggar is gonna generate, or Suggar++, excuse me, is gonna generate, is gonna reside in that directory. So the input directory contains this input.xml file, and that contains all of the elements that Travis is describing in the node tree. There's a variety of log files. The other conspicuous one you should notice is the DCI file. That's one piece of information we definitely need for Caelus. And then the other one is this composite.foam, which is a directory. That was the composite mesh element that Travis was talking about earlier, and that actually contains the polymesh. So this is our very familiar polymesh. So all we need to do is take the polymesh and the output.dci file, and we use that to go and build our case around. So on the right-hand side in the terminal, I'm showing you the setup of that case, and very familiar. It doesn't look any different than any other case, except for the fact that we have to first put the polymesh that Suggar++ generated in the constant directory, and then in the root of the case we put this output++.dci file, and so that's no change. Everything else is completely the same. So just really want to reemphasize that point. Okay, Travis, next slide. So I talked about the first point already. The other kind of small thing you need to do is when you're running in parallel, it requires a cell decomposition map, and that's available in the currently there's no change to any of the utilities to do that. You use the decompose bar, which is the utility for splitting the mesh up for parallel processing. You just provide it with the cell dist option, and that'll create a cell decomposition file in the constant directory. And I'll just mention this again. I think Ralph really covered that pretty succinctly earlier. Is for overlapping surface meshes, Suggar++ and Caelus will automatically compute the forces correctly on the bodies. You don't need to worry about any sort of double or triple or quadruple, whatever, counting on the body. That's all taken care of under the hood. So just be assured that the forces you're going to get should be correct, at least within the the solution code that you've generated. And then with regards to post processing, I think all the major and even open source post processors they can import OpenFOAM files, which Caelus generates OpenFOAM files for all the solution quantities. And then to help facilitate the overset, there's an iBlank field that's generated as well, and that's just a scalar field full of integers, and you can use the iBlank to disable the whole cells. And so go ahead to the next slide, Travis, and I'll show that. So here I'm just using ParaView just to kind of highlight this. So in the filter pipeline on the left-hand side in the panel, maybe a little hard to see because the text is small, but there's a filter there. It's called iBlank dash threshold, and that's a threshold filter that I use the iBlank field to disable the display of the whole cells, and the whole cells have an iBlank of 0. All the non-zero values are active cells, and so that's kind of what I'm showing in here. So when I took a cut through the mesh, we don't see any of the cells inside the car body, and we see some of the flow solution on the overset. And I'm just going to show you a couple more just to kind of talk a bit about some of that as well. So go to the next slide, Travis. So here I'm just showing, this is the surface pressure contours. Look, again, just no real change in typical in the typical post-processing process you can do here. It looks fine. I'm just showing the overlap serving meshes and the surface pressures. And then the last I'm going to show on the last slide, Travis, is some streamlines here. And so again, ParaView just naturally handles this, and all the other commercial processors. The three big ones in the CFD world at least are FieldView, TechPlot, Insight, and there's also other open source ones. Another one that people commonly use is Visit. So again, computing these streamlines, no problem, even though there's overlapping volume meshes. I should just point out you can kind of see a little bit of a rendering artifact here around the boundary of the background grid around the car, and that's actually just in the coloring. And the reason why is that this is just an artifact of ParaView, is that when you go to color streamlines, you can only color by point-centered values. Now, OpenFOAM and Caelus being finite volume cell-centered codes, the solution actually resides at the cell center, not at the nodes. And so ParaView is just doing some sort of background averaging to the nodes, which is not technically correct. So you get a little bit of this artifacting on the. So this is just purely a visualization thing. This is not anything you're going to actually see in the solution. So just before I let Travis wrap things up, I just want to mention a little bit about availability of what we're doing with regards to Overset and Caelus. We're just actually currently finishing up, working hard to finish up the remaining development on it. Again, I was talking about really kind of making available all the capabilities that people have come used to in Caelus and OpenFOAM, and to be able to do that, we had to pull a lot of this capability through the library, and so so that's what we're kind of working towards now. I think we're gonna work towards a staged release. The initial release will be just static grids, and then we'll move towards a prescribed motion, and then full 6 stuff. And right now, it's looking like Q1 of the upcoming year for the initial release. So if you have any more questions about, details about, how it's going to work and how it's going to play out, and some of the details, yeah, please go ahead and contact us. We'll be happy to talk to you about that offline. Okay, Travis.
All right, so you probably didn't hear what I was saying because I had muted myself, so now I'm unmuted. I just wanted to say thank you all for attending this webinar, and that a recording will be available by this Friday on December 11th, and you can access that by visiting our website, pointwise.com/webinar, or our YouTube channel. We're going to stick around for some questions for a little bit, so you can type those into the questions dialog box, and we'll get to those in just a minute. But if you have any questions that didn't get answered during this webinar, please feel free to contact us. If you have any questions about Pointwise, please feel free to email me at letstalk@pointwise.com. If you have any questions about Suggar++ or Celeritas Simulation Technology, you can email Ralph Nowak at sales@celeritassimtech.com. And if you have any questions about Caelus or the services that Applied CCM offers, please feel free to email Chris Sidoroff at caelis@appliedccm.com. And I'm going to leave this slide up for the remainder of the webinar while we're doing Q&A, so you can either bang out an email or jot these emails down while we're handling questions. So with that, we'll open it up for questions, and I already noticed that there are a few. So I will, looks like one of them has actually been answered in the webinar. So the next question is, how does Suggar++ handle very, very small clearances, i.e. tip clearances seen in screw compressors? And Ralph, there you go.
Yes, I'm here. That can be handled in a lot of ways. Mostly what is done is to provide enough grid resolution in that gap so that you would have sufficient overlap. And with the exact or very tight hole cutting capabilities within Suggar++, that shouldn't be a problem. You just have to have enough overlap between the two meshes.
Okay, thank you. And the next question is, can Caelus handle non-air fluids, for example, refrigerant, and can Caelus do multi-phase simulations?
Yeah, so the answer to those questions is yes. So Caelus, it can handle, effectively any fluid type that you want to specify. That's just, again, this is part of the kind of the runtime selection mechanisms that are available in Caelus. So yes, that's not really anything Overset specific. And then with regards to doing multi-phase simulation, it can do multi-phase now. There's a variety of different ways to do multi-phase depending on what type of physics you're trying to capture. But once we complete the full integration of the Overset into Caelus, then implementing whatever solver type you want using Overset would be possible. So yes and yes, or yes and yes in the near future.
Okay. Is Suggar++ Overset capability accessible via Pointwise glyph scripting? And the answer to that is yes, you can access that and set up everything through glyph. Everything in Pointwise can be automated through glyph scripting. The next question is, what's the difference between GGI and Overset grid generation?
So GGI, I kind of alluded to the whole GGI, which stands for General Grid Interface, and that is available in another variant of OpenFOAM called Foam Extend. So it's effectively a way to do these sliding interfaces I was talking about, doing prescribed motion cases where you have a rotating zone and a stationary zone, and the way that can be handled is with this sliding interface called a GGI, or in the vanilla OpenFOAM it's called AMI, Arbitrary Mesh Interface. And so I guess in a very philosophical sense, they're kind of similar, except again in the sliding interface, mechanism, there's expectation that the overlapping surface meshes in those regions, and in particular for rotational motion, they have to be cylindrically shaped. That the shapes of those overlapping surface meshes are very close. They can't be very different, or otherwise you're going to run into difficulties with interpolation and errors across those interfaces. So I guess the big restriction is restriction on the shape, right? And nothing can really pass through it. Whereas overset is much more general, that there's no notion of restriction on the shape of how it's overlapped. And so again, in a general sense, I mean, overset does also require that, or at least good quality overset requires that the overlapping cell volumes, the donors and receptors should be of comparable volume, but again, there's no real restriction on the shape, so it is much more general. So like I was talking about in the case of that rotating wheel, it would be very difficult to put in a rotating interface in that tiny gap and still maintain good quality mesh. Whereas overset, it just there's no such restriction on the shape.
Okay. Let's see. Where's the next one? Is Suggar++ a separate commercial software, or is it included in our Pointwise license? The answer is it is a separate commercial software. We've integrated with Suggar++ and Pegasus, and so you can set up the input deck for those two overset grid assemblers within Pointwise, but you would have to acquire them separately. Let's see. Okay, here's a really good question. Maybe Ralph or Chris might have an answer for this one. So how is manual color blocking adapted during relative motion simulations, particularly when the intersection between the surfaces happens to be changing?
Ralph, you want to tackle that one?
Well, sure. One way that can be done is by using deforming meshes. So your color would conform to the two surfaces, and that mesh deformed with whatever mesh is moving, or surfaces, the geometries is changing.
Okay. Let's see. Another one is, will any part of the overset capability in Caelus be subscription only?
I guess that's a good question. I mean, yes. I mean, it will be effectively the solvers. I mean, are going to be subscription only. I mean, and the reality is that using them still requires a Suggar, which is requires a commercial license as well. But yes, I mean, the answer to that question very quickly is yes. It will be. I mean, Caelus itself, as you see it, like how it runs, just like OpenFOAM, is freely and openly available. And in fact, people that are using it in that kind of general sense, we're actively encouraging people to contribute and add code or help out with this. But in this capacity, doing the overset, since we're working with Suggar and Celeritas, that the actual overset capability will be available through a subscription service that's through Applied CCM.
Okay. Does the Caelus overset capability use implicit or explicit block coupling during the linear solve step?
That is a good question. I'll have to ask my partners directly about that. I know there's a direct matrix manipulation, so I guess it would be handled implicitly, but we're still kind of we've taken one particular approach for doing that, where I mentioned I guess so it is still implicit because we're manipulating the matrix directly, at the overlapping overlap locations. But there's also some alternative ways that we may have to consider depending on solution quality and solution stiffness. But yep.
Okay. Are there any other questions? These have been really great questions so far, and pretty much everybody is still online. So if you have any other questions, please type them in. I have one that I can ask. So Chris, you put together this mesh, and I mean you're familiar with Pointwise. You've done some unstructured hybrid meshing, you've done overset meshing, you've done structured meshing. How would you compare the effort of creating an overset mesh with something like, say, multi-block structured, and then with something like T-Rex?
So it probably falls somewhere in the middle. I mean, the reality is, I mean, for simple geometries, you know, maybe they're all comparable. But you know, as the complexity goes up, you know, multi-block structure just, you know, the time takes kind of goes to infinity. But in unstructured meshes, you know, even for complex geometries, unstructured meshes can be time-consuming in the sense that the first mesh you generate can be very quick, but then you wait for the unstructured mesh to generate the volume mesh. You know, interrogate the quality, and then you have to go back and modify it. So probably in terms of overall effort and time, I mean, if I were to kind of this is maybe a bit completely arbitrary, but just to kind of give a rough, maybe a rule of thumb is at least on something complex, I would say, okay, if multi-block structured mesh took 100 units of mesh generation time and the unstructured meshing approach took 1 unit of time, then maybe the overset is maybe 10 or something like that. It's you know, significantly easier than multi-block, but it's, you know, I mean, it still requires more effort than, I'm not going to hide the fact that it takes more effort than unstructured. But like I mentioned earlier, is that there still seems to be a lot of motivation and effort going into generating multi-block structured meshes, and so I think that, you know, in that sense, it provides a significant improvement in mesh generation time.
Okay. Has overset grid generation been tested on, or an overset grid been tested on GPUs?
No, we haven't gone that far yet. Well, we've done just only some experimental work on GPUs with Caelus in general, let alone overset, and at least on the solver side, but maybe Ralph can comment on any overset grid assembly work on GPU.
Suggar++ has never been run on a GPU, and I don't know that any of the overset other software that you might be finding has been run on it. So,
okay. All right, Ralph, this is a continuation with the original question, and since you answered it, is if you can't use a deforming mesh for the motion of bodies with a manual collar grid, how would you go about doing so?
If the bodies are in contact, Suggar++ supports the identification of cells that could be treated by an appropriate solver using an immersed boundary method. So it's a way of kind of doing things without a collar, but you would have to have that kind of immersed boundary method capability in your solver to approximate the geometry that's defined in one grid by cells in the region in another mesh.
Okay. How do we measure the quality of the mesh? I'll just take this one. There's a lot of different examine metrics in Pointwise that you can use to measure the quality of your individual blocks, your components. There's also a handful of I think there's area ratio and volume ratio for your different components in your overset meshing. So you can look at the quality of those as well, particularly in the overlap location. As you saw, we actually in Pointwise pulled up a cut plane and we were looking at fringes. You could also look at donors and see where what blocks donors are coming from for your overset grid assembly. You can also look at your not only fringes like we did, but also your orphans, try to identify where those are and mitigate those problems. So there are a lot of different metrics that you can look at in Pointwise for your grid. Let's see, what about, oh yeah, can you apply overset meshing to unstructured grids?
Yes, because the composite mesh format that Suggar generates for foam it's naturally unstructured. The component grids in this case, the Pointwise generated were structured, but even when remember Travis talked about setting up the component grid file type, that was Cobalt, which is an unstructured format, so it goes out unstructured. So yes, you can easily do unstructured, I mean, like TET or Prism or whatever you want, yeah. And just in this case, we were just trying to use hexes to demonstrate the high quality nature of overset.
Okay. Okay, here's a pretty good question. This kind of follows along with the question you answered, Chris, about structured and unstructured, and it's what is the disadvantages of overset grid generation and CFD in comparison to multi-block or unstructured from your point of view that you think must be addressed?
Yeah, it's a very good question. It's not always easy to answer those, like, in a black and white sense. I guess it just really depends not only on your application but also your needs. I mean, ultimately you have to answer the question, what are you after? I mean, what quantities, how much time, how much budget do you have available to achieve not only the quantities but an acceptable level of accuracy, right? I mean, so, you know, uh, again, clearly the motivation for the CFD world to move to unstructured is just the need to be able to generate, reasonable quality answers in a much more feasible time, and particularly as the mesh complexity, the geometric complexity goes up. I mean, it's well known that multi-block structured meshes take far too long, and there's been really no kind of reliably automated way to be able to generate them. So, you know, um, I guess that's, definitely Overset fills that gap. I mean, but, I guess in the sense from a numerical point of view, it's doing interpolation. I mean, like, anytime you do interpolation, you're always going to incur error. Right? There's just no way around it. I mean, you can't interpolate perfectly. You have to accept a certain amount of, depending on how you're interpolating, you can only do so with a finite amount of accuracy. So anytime you're doing interpolation, there's the possibility of error, and so you just have to be aware of how much it is and where it's going to be, and try to mitigate those. So I know there's a pretty generic response, but I mean, it's just again very application dependent, and also, what are the needs of what you're doing, your organization or your project or whatever it is what are you seeking, and what are the constraints within those projects.
Okay. There's a question about using extrude or creating blocks manually, and I noticed that there was another question about setting up the input XML file in Pointwise. If you do have questions like that are very specific to maybe some things that you found in the software that you may have encountered a problem with, or something like that, or you want to learn a better way to use the extrude command or manually set up blocks, we have not only the videos on our YouTube page, tons and tons of videos describing that, but you can also contact us as a customer of ours. You can contact us. Just feel free to reach out to support@pointwise.com and talk with one of our support engineers, and they'll be able to point you in the right direction. What methods of interpolation are used by Suggar++? Some examples: linear, inverse distance, or both.
The Suggar++ has several different options that you can use, depending upon whether it's node-centered or cell-centered. For a node-centered, it is just using a standard linear kind of interpolation for most cases. I'll leave the higher order interpolation for structured meshes separately. For cell-centered cases, there's different ways of computing the interpolation weights. The best is to use the option which has a least squares procedure. There is an inverse distance weighting averaging, but I wouldn't really call that interpolation. I prefer the term just an averaging, and it's at best first order. And then there's another least squares kind of procedure in there. So the default is a second order kind of linear interpolation. For higher order interpolation on structured meshes, we do have a general polynomial interpolation. So you can get arbitrary order, but your stencil width for the interpolation goes up with that order, so you can quickly get some very large donor and interpolation requirements in that. So hope that answers it.
Thanks, Ralph. Okay, on this particular sedan application, do you have any data correlating the solution from this overset grid to a solution from a unified unstructured grid?
No, and the biggest reason is because this is actually a contrived case. I mean, well, the sedan body is not. It's an old kind of benchmark case from the automotive world for way back. I think it's called the Ford C1. But the actual wheels themselves and the wheel wells and all that was all just created by me within Pointwise, actually, with some of their geometry creation and manipulation tools, just to create kind of a more realistic looking sedan case. So no, but I suppose it could be, but there would be no way to get any experimental data for it unless somebody somehow went and built all that. So no, not at this point.
Okay, Ralph, here's one for you. Can you talk a little bit about the wall distance calculation that you'd happened to mention at the beginning of your presentation?
I assume the distance to the wall calculation used in the donor suitability function.
Yes.
Yeah, that's just another quantity that Suggar++ computes. It is a distance to the wall. We've got a fairly efficient method of computing that, and it is computed from any point in the mesh to any wall point, and just stored at the grid points, and then used as part of that donor suitability function if you desire. It can be used as the complete donor suitability function, so the interface interpolation boundaries would be midway between the different bodies, or a really powerful technique is to switch and use distance to the wall near a wall, and then switch to a more conventional volume or something else for the DSF away from those walls. And that really helps maintain good quality interpolation boundaries, etc., in tight gaps and where you have tightly clustered cells.
Okay. Any other questions? Still quite a few people online, so if you have any questions, please type them into the questions dialog box. Here's a question. Can you comment, excuse me, comment on the parallel efficiency of running overset grids?
I mean, I don't have any exact data to give you to confirm what I'm about to say, but I mean, the way the overset is implemented, I mean, there's really nothing dramatically different that's been added to it to be able to handle overset. So, I mean, if you on the system you have available to you, I mean, whatever the parallel efficiency on a regular case, it should be just naturally the same for overset. So there's again, without doing some own testing to make sure that what I say is accurate, but at least I don't see any reason why it should be any worse than what you currently observe with your current system.
Okay, we're going to stick around for maybe just a couple more minutes and answer any questions that come up then, and then we'll log off and get the recording up. Okay. All right. Well, with that, we'll wrap this webinar up. And like I mentioned, a recording will be available with the full Q&A that we've just done on our website by December 11th. You can access that from pointwise.com/webinar or on our YouTube channel. And again, if you have any questions after this webinar, you can email us at those addresses that we've left up above. Again, thank you all very much for attending, and we'll see you in the next one.